Hello, my name is Ben Shappee. I'm a Hubble Fellow here at Carnegie Observatories, and I'd like to tell you today about my recent paper entitled The Nearby and Bright Type 1a Supernova ASASSN-14LP.
Type 1a supernovae are among the most luminous explosive events known and are visible from halfway across the universe. However, even though they have been used to discover the accelerating universe, the nature of their progenitor system remains unknown. It is generally accepted that supernovae involve the thermonuclear explosion of a carbon-oxygen white dwarf, but the basic details of this picture, such as the nature of the binary companion and the sequence of events leading up to the supernova explosion, are still hotly debated. A popular model for the progenitor system, known as the single degenerate scenario, is illustrated here. This scenario has a carbon-oxygen white dwarf accreting material from a non-degenerate companion until it reaches a critical mass when it explodes as a Type 1a supernova. In this model, the supernova ejecta will then strike the companion, creating a shock which may be visible for the first few days after explosion. Thus, supernovae caught extremely early may be used to constrain their progenitor systems. The All-Sky Automated Survey for Supernovae, or ASASSN, scans the entire extragalactic sky in both the northern and the southern hemispheres roughly once every 2 to 3 nights in V-band down to a limiting magnitude of 17. On December 9, 2014, we discovered a new source with a V-band magnitude of 14.9. This source was 1 kiloparsec from the center of the galaxy, NGC 4666, which is a member of the Virgo cluster's southern extension. We designated this new source ASASSN-14LP, and we released its coordinates to the community less than 5 hours after the discovery images were taken. We then classified this object as a Type 1a supernova less than a day and a half later. In this paper, we present new prediscovery data as well as follow-up observations covering 100 days after discovery.
However, to place constraints on the interaction between the supernova ejecta and a possible companion, we first need to determine the explosion time. We did this in 2 ways.
First, we fit a power law to the prediscovery and early time follow-up photometry of ASASSN-14LP to determine where these fits have zero flux. The prediscovery data came from both the northern and the southern ASASSN units, as well as the Japanese amateur supernova hunter Koichi Itagaki. The early time follow-up photometry were acquired by the Carnegie Supernova Project, Liverpool Telescope, LCOGT Global Network of 1 meters, and the Swift Space Telescope. We found that we discovered ASASSN-14LP just 2 days after first light, and we detect the supernova in observations acquired more than a day earlier. Second, we used the expansion velocities of the early time silicon and calcium absorption features present in our spectra to fit for the explosion time assuming the power law relationship presented in Pirro and Akar 2014. These observations were acquired with the MDM 2.4 meter, the Apache Point Observatory 3.5 meter, and the Fred Lawrence Whipple Observatory 1.5 meter. The explosion time we found by this method is about 2 days earlier than the time of first light we determined by fitting the early time light curves. This discrepancy points to a possible dark time between when the supernova exploded and when it began to brighten at optical wavelengths. We then used both of these explosion time estimates and our prediscovery data to constrain the presence of shock emission between the supernova ejecta and a possible companion. Here in our figure 8, we constrain the radius of a possible companion depending on the actual explosion time. If the explosion time was near that determined by fitting the absorption lines, our observations rule out a companion larger than about 1/3 the radius of the Sun. If the explosion time was closer to that determined by fitting the early time light curves, our constraints are weaker. However, for all reasonable explosion times, we rule out the presence of a red giant companion.
Although ASASSN is not specifically designed to find supernovae as early as possible, the discovery of ASASSN-14LP less than 2 days after first light is quite encouraging. Furthermore, the previous ASASSN epoch, taken less than 1 day after first light, found that ASASSN-14LP was 1.5 magnitudes above our limiting magnitude. However, we did not trigger on this observation because of poor weather conditions. But this does lead us to question, what is the earliest that ASASSN could discover bright nearby supernovae?
To address this, we used our early time power law fits of ASASSN-14LP to determine that we would have been capable of detecting this supernova just 9.5 hours after first light. Thus, for bright nearby supernovae, cadence is the limiting factor. Unless it is more rapid than every 10 hours, deeper surveys do not have an advantage over smaller aperture surveys. In addition, ASASSN has greater sky coverage than its larger aperture counterparts, which allows us to discover nearby supernovae over the entire sky.
If you'd like to know more about our work, please see our paper which is posted on the archive. Thank you.